went to 41 days. Yeah, if you've done any of this experimental kind of work, you know that last minute does not work at all, right? There's nothing I can do if you come in like 2 days before the project and say, I need help, and these things take time, right? So this paper, the reviews, some of you still were giving the standard sort of third person saying they did this, they did this, they did this, they did this kind of stuff, right? And I think the paper is fairly well written. How many of you thought the paper was fairly well written enough in terms of what they were doing kind of stuff, right? So I think all you have to do is like look at the, whatever they italicized. Whatever is italics was basically what the summary was. So you can write a summary by basically copying all the italicized words and then twisting it to change it into your own words, and that's that, right? But that doesn't really tell us what you want to know. So I'll send individual feedback for those people trying to improve the feedback. But for rest of about half of the class had a lot of good concerns, right? And we'll try to discuss those, right? And again, we look at it more in the context. I'm not so worried about the specifics of the particular hardware. Like some of you pointed out, these are old machines. They're not that old as the one we saw before, but these are still relatively old machines, and many of you may have never seen an Ultrix machine. So some of the stuff that we actually, in the paper, may not be applicable directly, but you want to look at the larger context, right? So the paper basically compares the memory system performance of Mac, which is a microkernel-based operating system, which eventually morphed into Mac, Apple OS X. Somebody mentioned FreeBSD too, but no, FreeBSD is still a monolithic kernel. FreeBSD is a different operating system than Mac, and the one that you see in the Apple has a FreeBSD server, just like the paper that we talked about here. The Mac one has a FreeBSD, a Unix shell, but it's not. It's a microkernel underneath. I'll have an illustration to show what the difference is, right? Difference is significant because even though it looks like a FreeBSD machine to you, it can also look like something else to somebody who's in the same machine, and we'll see how that, and that's true in Windows and all those things too, right? And their goal was to look at the memory system performance and see if the way you do the different kernels make a difference, right? And one of the things that it's interesting is this experimental kind of work. I mean, they're trying to do some measurements and all those things, which is sort of very similar to what you will do for your project, right? But don't assume that your project will be anywhere close to the thoroughness that they would have done, because this is a PhD thesis for somebody at CMU who probably spent like 6 years working on the project, right? So it's not going to be as thorough, but I still want you to ask those sort of questions. And many of you started to ask those questions, right? For example, browsing through the comments, one of the concerns somebody expressed was whether it's statistically valid, right? They don't explicitly say how many times they repeated the experiments other than they rebooted after every experiment and what have you, right? So statistically speaking, your taught in statistics that you should repeat enough number of times to get the results you want, right? How does it apply to these kind of experiments? How do you repeat? How would you come up with the statistically valid results in systems, right? What is your thought on how would you do that, including the person who had the comment, right? Who wants to? So today I'm going to point at people, right? So if I get no volunteers, I'm going to start pointing at people. So what do you think of the
validity or the?
How would you consider something to be statistically valid, right? You know what statistically valid is, right?
Yeah, I know.
So what is statistically valid?
That depends on the task you are performing on.
Mm-hmm. So how many times would you repeat an experiment to come up with the statistically valid results?
Yeah, we probably, if we have a number over there, probably have accuracy.
You hold what?
Decimals or the accuracy.
I'm sorry, I didn't catch. What did you say? The first part, right? You said if you hold what?
If we calculate some numbers, get a result, right?
Yeah.
And there will be a difference between two calculations or one calculation. You already use that. It's hard to get all the every time. It's hard to get the result every time, right? If we probably put 1,000 times 1 error, that'd be fine. If 10 times or error, no, it's not enough.
Yeah, so 1,000 times is one number, right? 1,000, repeating something 1,000 times would be a good number, right? How many of you think it's a fair number? How many of you think it should be millions? Or how many of you think fewer should be enough?
Oh, it's all depends on how long it takes, to do an experiment. So if you run well, if I run the control job, it takes like a week to run. It's not able for me, to run it, like 100,000 times.
So that gets to the practicality of it, right? The statistically valid point, I don't care what it takes for you, right? I mean, if you look at this from a publishing paper or explaining the results to somebody, right? I don't particularly care whether it takes you a week of your time to run one experiment, right? Right? To be statistically valid, you have to run it a certain number of times, right? But your practical aspects is noted. I mean, if it takes 1 week to run one iteration, 1,000 times would mean you need to run it for 7,000 weeks, right? Which may be too long for most of us, right? You don't want to. I mean, if you read the Galaxy, the Hitchhiker's Guide to the Galaxy, right? They run the experiment for like 5 million years to come up with the number kind of stuff, and most of us don't have that much time, right? So that's a valid concern, right? So you want to figure out. So that's the real issue that you see in all this work, right? You want to be able to experimentally repeat all the stuff over and over again, right? And especially here, there are a lot of variables that you don't have control over, right? If you're running a simulation, everything is controlled. Here, a lot of things are not under your control, right? For example, there may be cosmic rays which are affecting something that you're doing, right? So when you run it 1,000 times, you may see a difference because there's a cosmic ray stuff, right? I'm not saying it's happened, but it's supposed to happen with a certain number of probabilities. There may be issues with the voltage may be flickering or what have you. So even if you run it 1,000 times, you may see variability because there are other parameters that you have no control over, right? And they say that they kind of ignore some of those by rebooting the machine all the time, but the disk may be wearing out, the CPU may be, I don't know what's happening with the system. So even if you can run 1,000 times, right, to be statistically valid, they have to run a lot of times. But the practical aspects is people have to graduate, people have to move on, people don't want to do this for years and years, and machines are, so there are a lot of practical constraints, right? So you see some of this stuff where you don't really run it for 1,000 times. You maybe run it for one time because one time of all this experiment, they did a lot of different stuff, right? So you want to run all this stuff and you want to kind of understand what's going on and all those things. That themselves probably took them, like say, 2 years. So they didn't say it, but let's assume that they only did it once, right? If that took them 2 years, rounding it 1,000 times would take them a lot longer than they can afford, right? So that's a real concern, right? And so you have to make sure that you even though practically can only run it so few times, you still have done enough to convince yourself and convince others, right? That's not always an easy task. I mean, that's not a trivial task. And I really note the reason why people complain. But the other aspect, when you're writing a paper or something, you go like, but I can't possibly repeat this for 1,000 times because that'll take me 2,000 years, and I'm not going to run 2,000 years on the same DEC 5,000 series, right? So that's one of the reasons. The other stuff is, even if they say they run 1,000 times, right? A lot of the things that they say about the system, they can't possibly explain everything that they did, right? In all the stuff, the only proof is if they give you the exact source code, right? So some of you mentioned they want to know what the GCC version, like what kind of optimization GCC was doing for a different operating system, right? The assumption is it's probably the same because they're using the same version, but there are still other variations, right? So you'll have to say we use Ultrix 5.3.2.2. In fact, give you this whole source code. You have to give the microkernel source code. You have to make sure that everything is documented, right? And some of the stuff would be completely relevant. Some of them would be irrelevant, right? Like, when you're running the Mach experiment, the room was 45 degrees Fahrenheit. We're running the Ultrix one to 60 Fahrenheit, right? We don't know if that make a difference, but you have to document all the stuff, right? So what happens is at the end, you have to be able to kind of trust somebody with the stuff. And the other part is you can't repeat all the experiments, right? How much you would like to do, you can't go and repeat it. So if you're in theory class, and if it's a mathematical proof, all of you can go off and kind of prove or disprove what I said, because if I say 1 + 1 = 3, you can prove I'm wrong. But here, if I say something, you may not have the hardware. If you go back to 93, all of us may not have all the software, all the hardware to repeat the experiments. So we have to sort of trust the stuff, right? And so when you write papers and stuff, people are very skeptical. You have to be skeptical. I'm glad that you're skeptical, because you have to, at the end of the day, kind of trust them, right? You have to trust that they didn't do something which affects something. They mentioned that, in Ultrix, some of the device drivers were not optimized, right? And in Mach, they were optimized, right? What difference does that make? We don't know. We have to assume, and their good faith and our good faith, it's all okay. But you have to understand what's going on. The reality kind of gets in the way. And that sort of things you'll have to do for your project too, right? You can't possibly repeat something 1,000 times or what have you. 1,000 times collect all the data and present it in a nice form. But you have to convince yourself first and try to convince others that what you did is reasonable enough, right? Does that make sense, right? So I still agree that it's not statistically valid, but we can't ask them to run it for 2,000 years to come up with the statistically valid results, right? Somebody mentioned about the epoxy, right? So the other epoxy, and which is how they collected the data, and it slows down by 15 times, right? Which is awfully slow, right? And then they say how they get around that by simulating the stuff, right? And one of the other big problems with measuring real stuff is you easily perturb the system, right? Meaning when you run these experiments, when you put all this instrumentation, you slow things down because you're putting the instrumentation, right? So ideally you would like to watch it without touching anything. So you like to capture everything and then do stuff with it. That's not always possible, right? So one of the things that I've seen people do is they put probes on the memory bus and wires and stuff, collect all the data to see where the addresses are going, and try to figure out what's going on from there. And then you have a problem of how do you store all these traces? You have billions of traces, and how do you analyze all those stuff and everything, right? Each one of them have their own strengths and weaknesses, right? And it's good for you to understand what the strength is, and good for you to see whatever the step that they took, whether it sounds reasonable, right? But it's again a fact of life. How do you do that? How do we collect some data without perturbing the system, without modifying the system, right? And the one of the things that you pointed about Condor, right? So people do analysis of large-scale systems, right? So you would like to measure the performance on a 1,000-node system, right? How would you do performance on a 1,000-node real deployed system? How would you collect something from Condor pool of, what's the Condor pool size you have?
We had energy there, we had maybe 500.
Okay, so 500 nodes, right? How would you collect something about this stuff, right? Something, I don't know, machine load or something, right? How would you do it?
There are logs file that you can look at it.
Okay.
But I don't think we have a tool that automatically go there.
So let's go back to log file, right? How do you create this log file?
When you run it, it's automatically create a log file.
So now you're perturbing the system, right? No. Presumably, if you're not collecting data, right? They would not be running these log daemons, would they?
I think there's an option that you can, when you run the Condor job, you can specify, to write a log file or not. But I think for
but I'm saying if nobody wanted to look at the statistics, right, they won't log this stuff, right? Yeah. So the system that you are trying to study is different than the one that you are trying to observe, because to observe you need to log the stuff, right? So your program now has to log something, which is what it's trying to do here, and then you need to collect all that stuff back to you, which means you're using network for collecting the data, right? So you're perturbing the system, right? Whether it's good or bad, whether it's small or significant, is what you're trying to convince, right? You cannot argue that you did this experiment without changing anything, right? You can only say our changes were very small. In this case, the change is very significant. 15 times slower is awfully slow, but they have to kind of convince you. And whether you're convinced or not, it's fair to be convinced or not. That's part of what we are trying to do, right? And somebody mentioned the time waiting for I/O, and I think they addressed those, right? They don't specify how much time they're waiting for I/O, because they kind of ignore the idle time, because it depends on other factors like that, right? And somebody mentioned Mach failed, right? They say, they come out and say Mach failed, right? And I chose the word fail specifically here because one of the things that I want to get across in the whole class is there are two types of things you can do in an operating system, right? One is obvious thing, right? The other one is a trade-off, right? Obvious thing is if you find that in your system you're using bubble sort, right? And suppose you change it from bubble sort to quick sort, and your system performs twice as fast, right? That's not research that no one cares about, right? Because that's so, I mean, if there's no trade-off, if you simply change something and it becomes to run faster, then you're good to go, right? Whereas when you do trade-off, it'll look good on one thing, but it'll have to be good on something else. And so I think somebody pointed out that even though it looks like Ultrix was faster than Mach, history, how going forward, DEC actually decided to go with OSF1, which is actually a Mach, right? So DEC actually went to Mach, which is not the one that won the performance race on these experiments, right? So we have to understand what is the larger context, right? The larger context of what things happen. And this usually never failed or whatever. It depends on what kind of a thing you want to trade off. And some trade-offs are considered more important than the others, right? So maybe the marketplace decided performance was not the reason why you should care about this stuff, something else. And that what this paper was, right? So there is nothing called failure. There's only things which didn't work out for whatever you're trying to do, right? So it's all about a trade-off. So I would like to stress that, right? That it's whether the trade-offs you believe is good or not, it's one thing. If it's a purely dumb implementation, we don't talk about it because it's a dumb implementation. We fix it and move on, right? So the larger context of all the stuff is back in 90s and stuff. There's a lot of discussion going on. There's the notion of a monolithic kernel, microkernel, nanokernel. We'll see nanokernel in the next lecture. And the idea with the monolithic kernel was there's a lot of spaghetti code. There's put the code together into this big one big thing. And we talked in the last lecture about how you can layer it to make it more tangible to manage. But essentially they're coming to grasp with this notion of there's a lot of code for operating system and how do we arrange it. There are a lot of different things which came about, a lot of different technologies which come about, right? So let's see what is the problem being solved here and what's the thing. So one of the things that people talk about from that era is monolithic kernels tend to be big and bloated, right? They all rile about how monolithic kernels are big and bloated and how we're going to solve that, right? The question is, why is a monolithic kernel considered to be big and bloated? So what is a monolithic kernel? What is it? How do you define monolithic kernel? Okay.
Is it where all the operating system services are part of the same, I guess I don't know, part of the same code base or part of the same process? And everything's kind of put together at a single layer rather than split up.
Is that accurate enough? Hint, it has something to do with protection boundaries, right? Yeah. Yeah, either way. Okay.
Go ahead.
Yeah.
Is it that everything runs in kernel space?
Yeah.
As opposed to in the microkernel, only the most essential services run in kernel space and everything that can be run in user space?
It's part of both, right? I mean, when they say, so one of the things when they say it's bloated, right? You have to remember that if you want to do certain things and it requires operation A, B, C, D, right? Regardless of how you organize the operating system, you're not going to get rid of steps, right? In order to say, let's say, read a file from a disk, and for a given same file system, right? Reading a file may mean that you need to read something from the disk. You need to read some stuff. You need to do a certain number of operations, right? High level notion of operation. You need to say, find the disk, open the disk, pull the disk, and read the contents, blah blah kind of stuff. You're not going to be able to get rid of those, right? So when they say bloated, right, it's not like monolithic kernels. When you say read the file, it reads a file and then plays solitaire for 5 minutes and then gives results back to you, right? There is no unnecessary code inside the monolithic kernel any more than what is inside microkernel or what have you, right? So all you're trying to say is where they reside, right? So in monolithic kernel, they tend to reside inside the kernel, right? So you have one big kernel. So you make a request to the kernel. You as a user, from user mode, make a request to the kernel. And the kernel does everything to you and gives them back the results to you, right? So all the stuff that is necessary to do the stuff becomes part of this one big kernel, right? Whereas in microkernel, the assumption was the operating system is doing a lot of stuff that may or may not be specific. It's doing the policy and the mechanism, right? It's doing the policy on how to do stuff, and it's doing the mechanism of how to do the stuff, the thing, right? So can you think of an example of what is the difference between policy and mechanism within operating systems? What is a policy and what is a mechanism? To make it more clearer, let's take a file system, right? File system has the notion of a files to the user and write something to the disk, right? What would be an example of a policy in a file system? What would be an example of a mechanism in a file system?
Actually, the policy probably is the design idea before the implementation. A mechanism will probably just a way to implement that thing.
So say example with this context, right? Like more concrete example. What would be example of something which is a
policy for the file system? Yeah, we can read, we can write. We don't know how it goes. Mechanism probably you can treat everything as like a link. So you can treat everything as a file. But in Windows, it's different. It's a different way to.
So what is the example of a mechanism in the file system notion?
Would it be like associating, so the policy being associating like a file path with the actual location in memory, but then the mechanism being actually going to that location in memory and retrieving what's there?
Yeah, I think that's a good definition, right? Policies can try to define what kind of a pages you assign into what, right? So when you take at the file system, I look at this as policy defines that you have this notion of like directories and all those things, like all the higher level concepts that you built on top of it. Mechanisms is you're operating on a disk. So mechanism in this context would be read and write disk, right? So you have to say go to block, read a block. That's all is the mechanism. But different file systems have different policies of how to organize the disk, right? So if you think of the disk as a bunch of blocks, different file systems put different ways of treating the disk, but all of them eventually translate to modify operations on the disk, right? So mechanisms would be read disk, write disk, read a block, write a block. The policies would be different file systems, right? So their model here is separate those, right? Put the necessary mechanisms inside the kernel, right? So for example, in this case, let the kernel only do block read and block write, right? The kernel does not, the OS does not need to know anything else. So it'll give you mechanism to read a block, write a block, and you implement the mechanisms, the file systems and all those things as something outside the kernel, right? If we do this right, the microkernel would perform just the bare necessary things. So it will tell you how to schedule a process. It won't tell you which process to schedule, right? That's a decision that's a policy, right? So if you want to do LRU or whatever policy you have, that's not part of the kernel. The kernel can say, if you say this process should run and this process should not run, it can do the context switch very well, but it has no way of knowing, it does not care why you chose two of those stuff, right? So the notion here is you make the kernel only do stuff like schedule a process, not choose which process to run, write a block, not choose which block to write or choose which blocks should be gathered together or what have you. So you kind of split them into this notion of the core of what needs to be done, just the mechanisms, optimize them, and move everything else up, right? So that's the notion. The idea here is then that means you can optimize the microkernel to be extremely good at what it's trying to do, right? It depends on the fact that this division has to be smooth, right? If you want to implement a policy that cannot be implemented by the underlying stuff, then the thing is a failure. So you want to be able to do that. And the side benefit is now you can implement different mechanisms on top of this stuff, right? Sorry, different policies on top of the same system, right? So for example, in Windows, you can have Win32 and POSIX, another different way of doing stuff on top of the underlying kernel, right? And if you do it right, your machine can act like a Windows and the Mac and the Linux at the same time because they're all underlying all of these operating systems. All the operating systems write to disk, right? They write blocks to disk. That's it. So you can make them all coexist, right? The challenge here is people sometimes confuse what these things are trying to do with what is the word micro, right? I don't like the word micro because it seems to imply that it's some sort of a small, right? So is it really important for this to be small? What do you think? So there are two different ways of doing this stuff, right? So if you think of this in monolithic kernel, this is kernel space, and this is user mode, right? And you have your apps here, and you request service from your kernel. How do you request your service from your kernel?
Yeah. Monolithic? In monolithic?
Yeah.
System call?
Yeah, so system calls, right? Again, these are stuff that you should learn from your undergrad, right? So you have system, you do this stuff, right? So anything you want from kernel, you make a system call and it given back to you. You don't have no idea what's going on. So what they tried to do that is replace this. You still have the user application, right? User application is not going to go away. You want to have a little thing called kernel, right? And this is a microkernel. And traditionally it's showed as like fairly small, right? And you move stuff here in application space. It does not have to have protection. All they're doing is they're making decisions on what should happen, right? They're making decisions on mechanisms. So you don't have to worry about protecting them. You have to protect the policies, not the mechanisms. Sorry. Okay. You have to protect the mechanisms, not the policies, right? Why? So okay, I'll come back to the question in a little bit, right? So what they're trying to do is they move all the policies here, right? They have a policy here. They have a policy here. You may know this policy as Win32. You may know this policy as POSIX. You may know this thing as NTFS or whatever, right? And over here it deals with blocks and all those things, right? They are outside the kernel because they're in user mode. The idea here is you have some sort of a library here, and it's there because you want mated compatibility, right? So you no longer have to talk to the stuff. You continue to work like you did before. So this library captures all the stuff, and it calls whatever the kernel, and the kernel may call into the appropriate application, and they may call back, and they may call here, call back, and eventually the answer may come to you this way or what have you, but eventually it comes to the application like this, right? So this is essentially what you do with the microkernel. You kind of have this notion. So if you do it right, you can move the stuff out of here, right? And the good thing is you can add more stuff if you want it. You can run it in the same machine, Win32 and POSIX if you want it. You can get rid of this, right? And your system will still perform, right? So you can make the system as small as possible by just keeping few of these stuff. You can make it big by having all kind of stuff, right? You can run all the, I'm sure there's no reason to run, why you can't run Windows, Linux, FreeBSD, and all those stuff on top of Windows or Mac or any of those, because it's a matter of building this stuff, right? And what makes you think that you can move this into user mode, right? Or going back in monolithic kernel, why do you keep everything inside the kernel? Why do you have two modes? Again, this is refreshing from undergrad stuff, right? Why do you have why don't you use one mode? Why do you have two modes? Yeah.
To run applications or users from altering operations or behavior.
Yeah, so you want the system, you want some sort of a way to prevent users from modifying the behavior, right? So in this case, why is it okay to move the stuff out?
Because it's just policy. It's not any mechanism for actually doing anything. It's just the policy for how to do something.
Mm-hmm. So you have to be careful on how you do the stuff, right? You want to make sure that the stuff that needs to be done, that has to be done in a certain safe way, has to happen inside the kernel, is still protected, right? So, for example, I may let you figure out which block that is assigned to you want to write, right? So you're free to, if I allocate a block to you, and you are free to write whatever with it, right? So the model here is, if you want to trash it so that the system becomes completely unusable to you, that's perfectly fine, right? What they still have to maintain is you don't destroy the system. So this kernel will not let you modify a block that is not assigned to you. So it has to keep not just track of blocks, not just say like, okay, if you say I want to write block 4, I write it. It has to make sure that the block belongs to you. You have the privileges to write it. So it's not as trivial as saying, you tell me a block to write, I write it, right? You tell me which process to run, I run it. I still have to make sure that you run the stuff. You have the privileges. So you have, so it becomes a bit more complicated what goes here. But then I don't particularly care what you do within your own space. So if you want to trash your system, you should be perfectly able to do that. There's nothing which prevents you. So in microkernel, that's the reason why you do that. You save some things. I don't particularly care if you trash your system. So if you build your file system to be corrupting all the time, be my guest, right? That's not a concern that an operating system should have, right? And I think this we went through in the undergrad operating system class. How does that gel with your notion of what operating system should do? If Microsoft were to tell you that our kernel underneath is perfectly safe, it will not have any problems, but the NTFS file system implementation may have any number of bugs. It may crash the stuff, right? It goes back to when people complain about Windows crashing, right? Whose fault is it, right? And as a company, Microsoft cannot really turn around and say, well, we only guarantee that this kernel would be safe. We don't particularly care if you lose all the stuff because our user implementation of the file system is bad, right? So that's a political versus the technical reason, right? The technical reason is we assume that as long as you're allowed to do it, you're free to shoot your own foot. But in the marketplace, you can't really do that. And that's one of the reasons why you kind of mess things up, right? So essentially, this is what you kind of have in the microkernel, right? So what you really want in this scenario to work is you want this to be fairly fast and fairly robust and does all the things that you want, right? So for example, it should not let people who don't have privileges do the stuff. So it should understand some privileges, but not necessarily the policies, right? It should know that if you are a certain kind of user, or a certain user, you should give you stuff. It does not care how you authenticate yourself, whether you use LDAP or Kerberos or whatever. That's all in policies here, but it tries to figure out if you're the right user, it should let you do the stuff, right? And as you might notice, there's a lot of errors going back and forth, right? In the monolithic kernel, there's one error going in, one error going out, but here there are a lot of errors going in and out. So now you need a lot of ways for our processes to communicate with each other, and that's the inter-process communication stuff. So essentially, whatever you ask has to go into the kernel, come out, and go through all this stuff, and those become a big performance bottleneck. And that's some of the stuff you're seeing here in terms of these things going back and forth. Because let's say you want to write a file, right? So if you say write 1,000 bytes, the 1,000 bytes may come into this library, may go into the kernel, which may go into the NTFS stuff, then it may go into some data store or whatever. So it may be being bounced back and forth, and that is performance interesting. We'll see later on how we can address those, right? Why do we have to copy this stuff? So if I have this stuff, can I just pass a pointer to this data back and forth, or do I have to copy it into a different data structure? Meaning, can I pass a pointer here, or do I need to make a copy here and then send it? Again, this is undergrad OS. You must have looked into it. When you make even monolithic kernel, when you make a system call, do you make a copy of all the data and operate it within the kernel, or do you just use a pointer? How about you? Sai? I'm just picking names, sequential order, so.
For the system call?
System call or what have you, right? So if you make a system call, do you have to copy the data that you are, if you want to write a block, right? If you want to write 1,000 bytes, do you have to copy it into the kernel, or can you just pass a pointer into the kernel?
I think we should find the fastest way to do this. Maybe just send the pointer.
So how many of you believe that sending a pointer would be the right thing to do? So for the rest of the majority, why do you think sending a pointer is not a good idea? You have to have an opinion either way, right? So why do you think that sending a pointer is not a good idea?
Yes.
Or the one?
Or maybe the the data you want to write, somebody come in and change it before you can make it.
There are other issues, right? So when you send the data, you want to make sure that when the kernel is modifying it, you don't get to see it. Some other application tries to modify it, you don't want the kernel to see it, right? And there may be protection issues involved, right? Because remember, when it goes into kernel can modify anything it wants. So you cannot coax the kernel. So if I send the wrong pointer, kernel has all the privileges, it can do stuff. So you tend to copy the stuff, right? There are a number of reasons. Protection is one of the things. And the issue of if you have two processes running and one of them tries to modify it, you want to have some predictability. You want to say, I said write, just write that, not the contents which are being modified by another thread or whatever, right? So you could use pointers, but you have to be very careful, right? So in general, copying is easy because you don't have to worry about it. So once I make a copy, I don't care what you do the original because I have a copy. That copy, I can pass it around, right? Which means that now I'm creating lots and lots of copies which get bounced around, right? So when it comes here, the kernel has to make a copy, right? In sense of you make a copy here, and then you make a copy, and so on and so forth, right? So you copy this stuff, and that's one of the things that they noticed, right? That this copying kills you, right? Because you're now doing a lot of memory operations, which kills you in many number of ways, which are all they point out, right? It kills you in terms of you lose memory locality, you lose write locality, you lose TLBs and all those things. So copying is bad, right? You would like to avoid copying, right? And the question is how relevant, how inherently, how much of it is part of being monolithic kernel, and that's the argument, larger argument that this paper does not exactly come out and say it, but that's relevant to why we're reading this paper, right? And so that we'll see as we move along. Which of this makes this kernel smaller? What aspect of this makes this kernel smaller? Or do you think that the code size is not really an issue? Do you believe that monolithic kernel would be bigger than microkernel, right? Obviously, it'd be bigger in terms of just the kernel, right? If you look at the monolithic kernel, by definition, it has to be bigger because it includes this and all of this. I mean, it includes this and all of this, right? And whereas in microkernel, if you only count this, right, it makes no sense for this to be bigger than this. Then it's like awful implementation, right? And Mark was some of it. Mark was not exactly optimized. Mark was not exactly, people didn't optimize it as big. So even though this was bigger than this one, proportionally it may not have been that much smaller, right? The challenge is trying to understand what is it that makes microkernels interesting, right? Is it the size? Why do you care about microkernels? And why do you care about monolithic kernel, right? And that's what we're trying to understand. And the other problem is, if you're going to go with the stuff, what is the one which kills you, right? And I think the subtext of what they're trying to say is that all this copying would destroy you, right? But you can get rid of some copying. You cannot avoid some of the overhead, right? Can you name one overhead I show in this picture which cannot be avoided however you do this stuff, right? If you do it through a microkernel, let's say you do this, you follow these arrows, and let's say you have monolithic kernel, right? Name one aspect of this picture that is going to give you overhead that you cannot do anything about. Yeah?
There's at least one context switch. So you're going to go from user mode in the application to kernel mode in both of them in the monolithic kernel as well. So you can't avoid that.
Yeah, you can avoid this one, right? But in microkernel, remember the kernel boundary is here, not here, right? So every time you bounce around like this, you're going to have a context switch, right? You're going to have remember the covered context switch from undergrad OS, right? So what happens when you do a context switch? Hey, that's a part of your undergrad OS stuff, right?
Program running gets swapped out of the processor, and the new one gets swapped in.
Mm-hmm. So you store all your state, and you take the new identity, and then when you come back, you restore all your state, right? Which may mean that you store all your registers and blah blah blah, and then you become somebody else. So you go from user mode to kernel mode, and then you store all the stuff that you had in your user mode somewhere, become kernel, do all you have to do, and when you come back, you have to restore all the stuff, and then you have to switch back from privilege to non-privilege. So every time you do this stuff, you're doing this overhead. You're doing overhead of saving and retrieving. However small I make it, it's never 0, right? So all the overhead you're adding here, you have to pay, right? Because you have to pay because that's part of what has to happen. Like one of the things we agreed was some things are privileged, so you cannot remove this boundary, right? The only way to optimize this is trying to make this as big as possible, right? So you can have it flexibility by having lots of these bubbles, or you can have performance by having very few bubbles, right? In fact, you can have one bubble with all the stuff and one stuff here, right? Which is sort of like monolithic kernel, right? So that's what happens over the years, right? When you think about microkernels in the larger context, the thing you really would love is to have this and have lots of little bubbles and say, this is for POSIX32, this is for NTFS32, and all those things. Have lots of bubbles here. And then it kills you on, I mean, it's very easy to maintain a system because you have all this little stuff. And all they do is, this is NTFS stuff. It interacts over here, right? So this interface is small because it only interacts with the file, only the file system context. It's easy to debug. You want to build a new file system. I change the policies here, and this is sort of the same. So I can build as many as I want, right? Once I do that, it's beautiful, easy to maintain. My performance is horrible because now I have all these switches, right? But then I say, oh, well, I don't want to do that. Just make this like bigger and bigger. And eventually come up with this one big cloud here, right? In which case it's monolithic kernel with a different name, right? So that's what happens, and that's really what is happening right now. What you see in your Mac or Windows or something are microkernels, but not necessarily, they're not doctrinal. They don't have an ideology that these things should be small. So they kind of in a mishmash between what they call microkernel and what is monolithic kernel you have right now, right? So there are a lot of subcontext of what is happening, and hopefully it's trying to fight the monolithic kernel versus the macrokernel thing. So the industry did go towards microkernel, right? And the reason behind was there is something to it. I mean, even though it looks bad on terms of performance, there is something to it in terms of manageability, right? And we are trying to find the balance of how big these things should be and all those things. To give you a sense, I don't know if you can read from the back, and this is basically from the Bershad's book, right? This is the Windows XP structure, right? So they essentially have the user mode split here, and this is the kernel mode, right? So they have a hardware abstraction layer, which means that they can port Windows to any machine that they want, right? The history behind it was back in the days, because of legal issues and stuff, Windows had to run on DEC alphas, right? So they had to make this hardware abstraction, which means that they can port Windows to any hardware that they want fairly quickly, as long as they write an interpreter for that particular hardware using a hardware abstraction layer, right? So they can run it on PowerPC if they wanted, because all they have to do is translate PowerPC to their hardware abstraction layer. Things are good to go, right? I don't know how well maintained this is because they only run on Intel x86, so this may not be that stuff here. Then you have the kernel, right? The kernel proper. Then you have all the stuff that you need here, right? The important stuff. They have object manager, they have security reference monitor, process manager, and all those things, which implement the mechanisms of what you have to do. Then on top of it, they have the user level stuff, right? So they have the Win32 subsystem, which can talk to the security subsystem, OS2, Win16, Win32, MS-DOS, POSIX. I'm sure there's some sort of version of Win64 or the 64 thing they're doing. So they can add all the stuff over here, right? So it is possible for your Windows XP to look just like POSIX, which is essentially what your Linux machine is, Linux kernel is, right? So if they wanted, they can make this stuff, get rid of all this stuff, and just run it as a Linux stuff, right? They won't do that for market reasons, but there's technically no reasons why they can't do this stuff, right? I didn't have a good enough picture for Mac, but essentially they have the same thing. They have the kernel environment, which is the Mac kernel, right? And they have different application level servers on top of it, right? So BSD is one of those. So when you run a shell, you're interacting through this stuff. So it looks like a free BSD, right? But the machine itself is not FreeBSD, right? Because the machine itself runs, what Apple runs is either Cocoa or Carbon apps, right? So those Cocoa apps are not built on top of FreeBSD, they're built on top of Mach, right? So if you use Mac, right, the Apple Mac OS, it's all the applications you build are top of Cocoa API, right? So they directly talk to the Mach kernel, not through FreeBSD. So it's not a FreeBSD machine. So you can't take a FreeBSD machine and port Mac on top of it. I mean, you could, but it's not trivial because it directly talks to this kernel, right? Of course, they have Classic and all those things. This is the stuff for Windows 2003 server, and essentially they retain the stuff. I mean, this is the kernel mode. This is the user mode, right? And there are user level processors or whatever which interact with the stuff. And you may see things kind of move back and forth, right? Depending on the performance, they may move stuff in and out. So system threads might have been outside, but that moved inside to get performance or whatever, right? So most modern operating systems are going this way. So the performance loss was not deemed as important as other stuff, right? And we'll see that there's some things you can fix. There's the copying and all you can fix. There are certain things you just can't fix. Actually, in the paper itself, they mentioned like some of the calls you can actually return directly from here, right? So if you want to look at a process ID of a particular process, this layer library itself knows it, so it does not have to ask the operating system. So it can give it right back to you. So in those cases, it's actually faster because there are some things it does not need to ask the kernel, right? So essentially, some of the questions that we were kind of talking about is what I had here. Like, you need to know the notion of why our kernels operate in privileged mode, right? That should have been covered in your undergrad OS, because that's fundamental to the notion of kernel and supervisor and context switch and stuff. So you should have looked at the stuff in the question of how do you go from the user to kernel mode, system calls, like one of you pointed out. And the notion of what really happens in all this stuff and what is important and what is not important, right? So if you get the impression from that microkernels are small, right? I don't think that's important because I don't really know what you mean by small, right? A lot of people use that notion that microkernels are smaller than monolithic kernels, right? Though it's strictly true, practically it has no significance, right? If you look at the number of source lines that you need to run this whole darn thing, microkernel may actually be bigger because now it has more of this abstraction and all those things. So you get lost in the discussion that microkernel is not about small, and it's more important when you go to the exokernel and nanokernel for the next lecture. I don't think the size of the code is important. I think the importance is how easy it is to manage the stuff, and managing is the good side things of it. The cost is all this copying and overhead and all those communications, and how do you deal with that, right? And so in the monolithic kernel, if you want to read at time, you have to ask the kernel, and the kernel responds back with what you want, right? Whereas in this case, it has to ask the library, which asks the kernel, can return the time. And the library can be smart and can return the stuff to you if it wants. But to write a block, right, I have to ask the kernel, and in the monolithic kernel, it comes back after it returns the thing. It has a policy, it has implementation, it does everything. Whereas in the microkernel, you ask the kernel, it may ask different stuff to figure out what the mechanisms are to be. So it may bounce around back and forth, and then it may give the answers to you. And the thing that they were trying to figure out, and the thing that we are still trying to figure out is, we love the fact that it's easy to manage, because we don't know how to manage a 50 million line monolithic kernel. So can we fix the performance? Can we make it better? What really happens with this stuff, right? Does that make sense? So they go through a number of assertions, right? The assertions, and they show that all the assertions are true, right? So I don't particularly care whether the assertions are true. I want to know what those assertions are and what they mean, because they apparently are important enough that they wrote about it, and apparently important enough that people liked it, right? So the first thing is, OS has less instruction and data locality than user programs, right? So what are they talking about, right? What is instruction and data locality, and why is it something that you should care about, right? So we have to assume that they are not doing this because they just could do it, right? Because, for example, if you don't know what you're talking about, you may measure stuff that has no consequence, right? So, for example, you reported that the deck 5000 was 10 pounds, right? We know that it doesn't matter whether it's 10 pounds or 1 ounce, right? In terms of the weight, right? So clearly these are important assertions, right? So what is data locality? What is instruction locality? Why is it important? You have to know the answer because this must have been covered in your undergrad OS too, right? So who wants to go?
I guess locality is the idea that if you access some block of memory once, you're likely to use that block of memory again in the future. And you're also likely to use something that's nearby it in the future.
So how does that, what is the term you use to describe this and use this stuff?
So I guess it helps with caching because it's sort of like if you take a block, or some piece of memory, it's wise to cache it because you know you're probably going to use it again. And it's also, as long as you're looking at the disk, you may as well take all the stuff around it because you'll probably need that soon as well.
You want to add something? So there's a notion of a working set, right? And that name should ring a bell, right? The notion of a working set and trying to figure out, the assumption here is once you access something, you're going to access it again. So you want to cache it because you, like you pointed out, hopefully it'll come back again. So whatever cost you paid once, you try to amortize it over and over again, right? So the whole goal here is you want to make sure you're trying to predict what you'll do in the future, and you assume that past predicts the future, right? So if you assume that since I access this instruction, I'm going to access it again, right? I can use that as a way of predicting the future, right? So I can sort of say, since I access this, I know I'm going to access it again, so let me cache it or keep it somewhere, right? The other thing he mentioned was if I'm doing a serial file access, I know I read block 1, so most likely I'm going to read block 2, right? So I can either predict in the future based on my past, or I can predict based on what I did, right? And they all depend on the notion of a working set, right? They all depend on the notion of working set where I kind of go through this stuff over and over again, and I will work fantastically well if my predictions are always true, right? If I assume that what you did in the past is indicator of what you're going to do in the future, and if it happens to be true, then I get maximum performance gains out of the system because I paid the expensive part once, and then I get the benefit throughout the system, right? So can you give an example of what kind of a... So there's a notion of instruction and data, right? So instruction depends on your program, and data depends on the data you're operating on, right? Can you give me an indication of what kind of a program would give you good data locality on the instruction side? What kind of a programming constructs would have good instruction locality? Yeah.
Loops.
Yeah, if you go through a loop, right? So what kind of things will give you good data locality?
Arrays.
Yeah, arrays are good. Traditionally good indicator, right? There are cases where arrays may not be, but usually arrays are good indicator, right? So that's what they're trying to say, and the assertion here is OS has less instruction and data locality than user programs. What does it mean? This is absolutely, yes, I.
It's hard to predict what you're going to need next.
Why? What's the intuition behind this assertion, right?
Probably the working set is very large because you have all those applications. And there may be some.
So they didn't go into the mark versus microkernel. I mean, okay, you're kind of jumping ahead, right? So ignoring the mark, microkernel, right? Why do you expect, or what is intuition behind expecting that user programs will have more data and instruction locality than operating systems? Yeah.
User programs are more predictable in the sense that a program does something, but if you have a loop or something, the operating system is much more complicated, and so it may run a loop and then go to disk and then do something else and then come back, and that's a lot more difficult.
So, did you get what you were saying? So you were saying that user programs tend to go in a small loop. Operating systems may tend to go in a loop, then go to another part, then go to another part, right? It does something for a little bit, then does something, then go to disk and all those things, right? So more technically, how would you say?
Working set of the operating system is much larger.
Yeah, working set is much larger. Our working set keeps changing often, right? So you can't kind of predict that, right? Does that make sense, right? So in the application case, you expect them to go through a single working set. Operating system goes through multiple working sets, or none at all, right? Does that sound intuitively true to you? What do you think a typical operating system, when you think of operating system does something, right? Think of anything you can think of. What do you think would happen, right? Let's say write a file to disk, right? Write a block. I mean, I say write 1,000 bytes, right? What do you think usually happens when you issue the system call? Okay, I have to pick somebody. Did I pick you?
I just talked.
Okay, so yeah, you can't do that. You have to. Conceptually, when I want to write a block, right? What happens? Everybody else wants to.
Well, it first has to figure out what it wants to write. So it has to copy the memory into some kernel space.
Mm-hmm.
Then it has to go over to the disk and say, disk, I need you to start spinning up so that you can start writing stuff. And then it says, okay, disk, here's the data that you need to write. And then the disk comes back and says, okay, operating system, I'm done. And then the operating system says, okay, application, I finished writing your 1,000 bytes.
And one of the things I think you maybe didn't stress enough was, you also have to look at some data structures to know where to write, right? So you have to keep some track of free blocks or whatever. And if it's free, if you find the right stuff, you write it. Some sort of data structure lookup, right? I think that's generally what happens, right? You look at some data structure to see what has to be done. Then you do some stuff which may be slow. I mean, this may be slow. You have to wait and all those things. Those are the idle time, and those are the non-idle times, right? One of the things that should have been stressed to you in your undergrad OS is you want to keep that stuff what it does to minimal, right? You don't want the operating system to sit up and ponder the meaning of world before it decides what to do, right? Because all of them is overhead. One of the reasons that you write operating system is you're not trying to find out the best algorithm, right? You never write the best algorithm to figure out what is the optimal block where I can write this data, right? That's another thing that you never do. You want to do as quick a job, as good a job as possible, because anything you do is overhead. So you don't want to do run a big AI program. So you tend to do as little as possible. Look at certain data structures, and then you kind of move on, right? I think that's what you're seeing here in reverse, right? What should have been taught to you in operating system was we never tried to optimize for cases where we don't need to be optimized. You don't try to optimize everything. If there's proof that something is very slow for all the cases, you try to optimize them. But in general, you want to finish it as soon as possible. Operating systems try to finish whatever they had to do as soon as possible, which means that they're not actually doing a lot of computation, which means that they don't have a lot of locality, because they possibly, they just look at some data structure here and then go into the disk structure, write something, and then get out. There's not a whole lot of things happening, and that's what you're seeing here. Do you agree with that? They say it as there's not much locality, and the reason you see locality when you see loops, like you mentioned, when you see loops, when you see arrays and stuff. And traditionally, operating systems don't really have loops. They may go through some data structure, but hopefully you don't have a million entry block structure where you go through every entry from 1 to million and come up with something. So you just look at some, like a couple of blocks, so you don't see the stuff. Another question that Nathan kind of asked, does it really matter whether it's microkernel or monolithic kernel? This notion that, so I read this as operating system really does not do that much, right? So there is not much locality because it's not doing that much to create locality. Locality needs you to have a working set, and there's not really that much, right? Does that change when you have monolithic or microkernel? Should it? I mean, should the philosophy of how they write that stuff should change? I think you shouldn't change. I mean, you still, whatever operating system does is what you want. Just because you have microkernel does not mean that you want to run an AI engine here trying to figure out what should be done. You still want to keep the same stuff. So I'm not really surprised that you're not seeing much thing because we still have the same idea. We still want to keep the stuff as simple as possible. We're not trying to run through massive arrays and loops and all those things. So you may not see the stuff. And some of this experiments that they did sometimes sound kind of fishy because one of the observations they had was sometimes it runs entirely in memory, so it does not have too much. There's not much I/O bounds. Some of the applications they ran, so the locality was not an issue because everything was in memory, so you didn't have to bring stuff in, so the performance was not so bad. And so the other flip side for the microkernel perspective, they said Mark had far less data locality than monolithic kernel. Why did that happen? Is it inherent to Mark or is it inherent to microkernel based system? In terms of data locality, so data locality, one of the examples is an array or some data structure where you go through, right? Why would there be less data locality in microkernel than a monolithic kernel? You can go back to this figure, right? So one of the things we mentioned was you have some list, free list or something to figure out what happens, right? So now we have this list all over the place. So there's something here, there's something here, which may be replicated here and here, but some different way of doing stuff, right? So from a system perspective, these all tend to be kind of scattered around. This is in kernel, this is in application space, this is in an application space. So even though they could all be related to the same task, writing a file may require looking at something here, looking at something here, looking at something here. They all might have looked happening at the same place in a monolithic kernel. Now they kind of spread out, right? So you still do the same amount of work as you did in monolithic or microkernel. You still have to look at whether the block is free. You still have to look whether the file system should allow you to do that stuff. But some block is done here, file is done here, something else is done here. So you kind of dilute the data locality, right? And that is a problem that will remain regardless of what kind of microkernel you have. Because the good thing is this and this can do independent stuff. The bad thing is this and this can do independent stuff, right? So how do you solve those, right? There is a solution. You have to figure out whether it's important or not, but that's essentially what is happening, right? The power is you don't have to do the same thing at the same place, but now you lose data locality. A lot of things you see here is basically you're making trade-offs which look good on paper on one count. It destroys your other stuff. And I love the paper because they actually go through and kind of articulate what happens, right? There's a lot of unintended consequences in what you do, right? You try to make something faster by doing the stuff, it destroys a TLB. You try to fix a TLB, then it destroys something else, and so on and so forth. And before I go to the next session, one of the nice things about this paper, which probably may not have, I didn't see anybody point out, is the graphs that they did. Like I was in the SOSP. This is my first SOSP back in '93, and the whole audience loved this paper because of the way they presented the data, right? If you look at the graphs, I mean, they did like 13 experiments, on looking at all the stuff, right? So if you just did the experiments and showed all the data, they can fill like reams and reams of paper with tables and graphs and all those things. So you can have, and you'll notice that for your project too, right? It's very easy to collect data. It's very hard to analyze all the data to find out what is important and what is not important. It's even harder to explain all those to you, right? So I can say this graph shows this, but you have to look at this other graph to show the aspect that I'm talking about here. So I need to have 3 graphs to explain what it is. Now I have 13 experiments. I'm going to show 13 times 3 for one assertion, right? But they did this beautiful, like this weird sort of graph where there's all these bands and all those things. So you can read this is from 13 experiments for 4 different parameters, all those things into one little graph, right? Which means that that graph should take you hours to to get what it's saying if you want to get all the data. Right? But it's a very compact way of representing data, right? And that's one thing that you appreciate. It's very, so when you see a bad paper, you see